So good afternoon. Welcome to the class of optical communication, and today we will discuss that one of the topic of optical communication, that is the meridional ray and the skew ray. We will discuss about the acceptance angle for the meridional ray and the acceptance angle for the skew rays. My name is Mr. Himanshu Nagpal, assistant professor in EC department of AKJC Ghaziabad. So first of all, we'll talk about the meridional ray. And the meridional ray, the ray which is launched into the optical fiber cable, and the plane which is the plane at which it is launched, that is should consist of the axis of the fiber cable. And even after the reflection, when the ray enters into the optical fiber cable, even after the reflection will, after reflection, the plane the ray which is traveling will also be in the same plane, and the ray, that's why that is the means that the ray is confined to the plane in which it was launched and never leave the plane, and that type of rays are known as the meridional rays. So let's say there are two types of rays which is traveling in optical fiber cable. First one is the meridional ray, and the second one is the skew ray. So meridional rays are the rays, let's say this is optical fiber cable and this one is the core, and outside this optical fiber cable, this one is the cladding. So when it enters, this is the axis of the fiber core, this is the axis of the ray which enters into the optical fiber cable, which consists of the axis of the fiber, which consists of the plane which is axis of the fiber cable, and after reflection the plane which never leaves its plane, and the ray, that ray will not leave its plane, and that ray will cross the axis of the fiber cable. That type of rays are known as the meridional rays. So let's say talk about the numerical aperture of the fiber cable. Let's say if I say meridional rays enter into the optical fiber cable at this, and this one is the optical fiber cable, this one is the core which is having a refractive index N1, and this one is the outside of this core, there is a cladding which is having a refractive index N2. This N2 is the refractive index of cladding, and N1 is the refractive index of core. Let's say the ray which is enter into the optical fiber cable is in the air, which is having a refractive index N0, and this ray, this is a meridional ray, this ray enters into the optical fiber cable and reflected at point B. This one is point B. The ray which is enter into the optical fiber cable, let's say the angle, this is known as a theta1. If this theta1 is the maximum angle which is enter into the optical fiber cable, then this theta1 can be known as will be known as the acceptance, half acceptance angle. and this ray reflect at point B and it makes an angle, let's say this, it makes an angle phi, and this angle is also will be phi. Clear? Let's say this point, this is point A, B and C. Now I want to calculate the numerical aperture, and before describing the numerical aperture, this numerical aperture is the ability of, is defined as the ability of fiber cable to collect all of the energy, all of the light energy incident on it, incident on it. It means this is the ability of the fiber cable to collect all of the light which is enter into the which is incident on the optical fiber cable. So the entry into the optical fiber, that depends on the entry into the optical fiber cable. That depends on the acceptance angle. Acceptance angle of ray. Means, what is the acceptance angle? This acceptance angle is known as the maximum angle at which the ray enters into the optical fiber cable, will be propagated inside the optical fiber cable and perform the total internal reflection. Means, if I say, let's say this is the acceptance angle for the meridional ray, so this is known as the acceptance cone. This one is known as the acceptance cone. If a ray, number of rays enter into this cone, will propagate inside the optical fiber cable and will perform the total internal reflection. But if the ray tries to enter into the optical fiber cable beyond the acceptance angle, then that ray will not be propagated, though it will be entered into the optical fiber cable, but that ray will not be propagated and will not perform total internal reflection. Clear? So let's say this is the ray at which it enters into optical fiber at angle theta 1. So apply the Snell's law at point A. Apply Snell's law at point A, that is air core axis interface. Clear? So if I want to apply the Snell's law at this point and it will perform the reflection, as we know that it means that n naught into me sin theta 1 will be equal to what? N1 into me sin theta 2, that is n naught into me sin theta 1 will be equal to n21 into me sin theta 2. Clear? Now see, from this angle, if I take this angle is right angle triangle and this one is 90 degree, this one is theta 2 and this one is phi. let's say this one. Clear? So you can say theta 2 is equal to 90 degree minus 5, or you can say pi by 2 minus 5. So just put this value, you will get n naught into my sin theta 1 equal to n1 into my n naught into my sin theta 1 will be equal to n1 into my sine of 90 degree minus 5. So this comes out to be, that is cos phi, and cos phi can be written as, using the trigonometric equation, cos phi can be written as 1 minus में sin square phi की power में 1 by 2. So it comes out to be n naught into में sin theta 1 equal to n1 into में 1 minus में sin square phi की power में 1 by 2. Now if I say this theta 1 is the maximum angle at which, beyond which the ray will not perform the total internal reflection, that means that this theta 1 is the acceptance angle. It means this theta, if I say for the accepting case, for the maximum limiting case, this theta 1 can be written as theta A, clear, and phi B will be equal to what? Critical angle. So it means I can write it as there n naught into my sin theta 1 is equal to n1 1 minus में sin square phi power 1 by 2 as it was from the previous. So I can say n naught equal to 1 and theta 1 can be written as theta A and phi can be phi C. It means that sin theta A will be equal to n1 1 minus में sin square phi C की power 1 by 2, and we know that critical angle is equal to sine inverse of n2 by n1. So putting the value of phi C equal to n2 by n1, so we will see that sin theta A comes out to be n1 into में 1 minus में n2 square divided by n1 का square की power में 1 by 2. It means on solving this equation you will see that sin theta A is equal to n1 square minus में n2 square, this is n1 square, this is n1 square minus में n2 square की power में 1 by 2. So acceptance angle will be equal to sine inverse of n1 square minus में n2 square की power में 1 by 2, and sin theta A is equal to the numerical aperture will be equal to n1 square minus में n2 square की power में 1 by 2. So we will see that theta A is equal to this one, as we have derived already this one, and numerical aperture comes out to be this one. Clear? Now this numerical aperture can also be derived in terms of the relative refractive index difference and the between the core, that is relative refractive index, that is delta between the core and the cladding, and we know that the delta is equal to n1 square minus n2 square की power n1 square minus n2 square divided by 2 into में n1 square. So you know that this one is what? Numerical aperture का whole square divided by twice of n1 square. So numerical aperture can be also be written as in terms of relative refractive index is equal to 2 into में n1 square into my numerical into my delta की whole power में 1/2 means the numerical aperture comes out to be n1 into my 2 into my delta की power में 1/2. So we'll see that the equation comes out to be this one. If the relative refractive index is very less than 1, means this delta can be written as n1 minus n2 divided by n1. So this one is the acceptance angle for the meridional ray. So I have already told you numerical aperture is what? Is the ability of the optical system to collect all of the light energy in one area, and you can say the numerical aperture of the fiber is the light collecting efficiency, means or ability of the fiber, and is a measure of the amount of light rays can be accepted by the fiber which is entered into the optical fiber cable and will perform the total internal reflection. So this parameter, numerical aperture, this parameter tells us also that how much light is collected by the fiber from the source. If the value of the numerical aperture is less, then smaller is the power accepted by the fiber cable, and if the numerical aperture value is higher, it means the maximum power will be accepted by the fiber. Now next one is the skew rays. As I told you that there are two types of ray which is entered into optical fiber cable. That is one is the will enter into optical fiber cable as a meridional ray, and another one is the as a skew ray. Now see, this is a skew ray which is not launched in a optical fiber cable in a plane which consists of axis of the fiber cable, means the ray will not be in the plane which is a axis of the fiber cable. For example, if the ray is launched at some angle such that it does not intersect the axis of the fiber, means as it is not launched into the axis of the fiber cable, and therefore it will not intersect the axis of the fiber cable, and then after total internal reflection it will go to some other plane, and it will go to the some other plane, and this therefore the ray essentially will spiral around the axis of the fiber cable, that is known as the skew rays. Means this ray will enter into the optical fiber cable which does not consist of the axis of fiber. Means if I say this ray, if I enter into optical fiber cable, this ray will be like this one, intersect like this one, and it will move to this one, though it will perform like this one. Means if I say this is an optical fiber cable, so the ray which is entering into optical fiber cable will be move around the axis of the fiber cable or along the boundary of the fiber cable, but will not intersect or cross the center axis of the fiber cable. Therefore it follows the helical path around the axis of the fiber cable. So the ray which is entered into optical fiber cable will be move around this helical path, means along the boundary of the fiber cable, and it moves in the forward direction. So this type of ray will not utilize the full area of the core, because it does not cross the axis of the fiber cable. It moves around the fiber boundary of the fiber cable. So it means it will not utilize the full area of the fiber cable, and this type of ray travel farther than the meridional rays undergo higher attenuation. this is a meridional ray, like this one will travel like this one, and this is a meridional ray, this is skew ray which is traveling like this one. So for the same distance, if I want to say, if I have to reach from A to B, the skew ray will travel farther than in reaching the same distance A to B. When it covers the maximum distance from point A to B, it means it will undergo higher attenuation, means absorption will be maximum in case of skew rays. Like this one is the helical path taken by the optical fiber cable. And if I want to take the cross sectional view of this one, means this ray will will move forward in the helical path. So from the center radius of the fiber cable, it makes an angle that is gamma. Clear? So now I want to calculate the acceptance angle for the optical fiber for the skew rays. Let's say this is the ray, that is skew ray, which is entered optical fiber cable, but will not cross the axis of the fiber cable. I mean, this is axis of the fiber cable. It will not intersect, means like if I say this one, this is axis of the fiber cable. Let's say this one is axis of the fiber cable, like this one. It will, like this one, move along the boundary like this one. So this one is the like this one, and this one, and this one is the core axis. This one is the core axis. Clear? Now see, this is a point A, this is point B. The ray which is enter into the optical fiber cable will be the, if I say this is a skew ray, let's say this enters at angle theta s and it makes angle theta this one. Now I already told you, this makes a angle of gamma with respect to this one. So this term, this will is the, after each reflection, this is what? This will be what? Gamma. Clear? Sorry, this one nahi, this one. This one is gamma and this one is phi. It will, after each reflection, it makes a angle gamma with the radius of the fiber core. Means this is the center axis, so this will make the radius, and after each reflection, this is not a gamma, this is gamma, this is will be gamma, and this one is a, let's say this one is phi. Clear? Now the reflection at point B at an angle phi, this can be written, given by the cos gamma into my sin theta will be equal to cos phi. So we will see that at this point, cos gamma into my sin theta equal to cos phi. Now can I written as cos gamma into my sin theta equal to cos phi, can be written as cos phi equal to 1 minus my sin square phi की power में 1/2 cos gamma into my sin theta. I can write it like this one. Now if I say for the limiting case, means the maximum angle, this theta s will become what? Theta as, and this phi becomes what? phi c. So I can written as this cos gamma into में sin theta as can be written as 1 minus में sin square phi c की पावर में 1/2. तो I can write like this one. This is cos gamma into में sin theta as is equal to 1 minus में sin phi c is equal to what? n2 by n1 का होल स्क्वायर की पावर में 1/2. Clear? So this is cos gamma into में sin theta as is equal to 1 minus में n1 square minus में n2 square पावर में n1 square की पावर में 1/2. I can write it like this one. Now see, if I say, so to eradicate this theta, there is a relationship between the theta and theta s and the theta. It means if I want to apply the Snell's law, we can get the relationship between the theta and the theta s. Apply Snell's law at point A. So you will see that this n naught into my sin theta s will become equal to n1 into my sin theta. Clear? So sin theta s can be written as n1 into my sin theta upon upon n naught, and n naught equal to 1 for air. Clear? So sin theta can be written as sin theta s upon में n1. Now put this value of sin theta in this equation. You will get cos gamma into में sin theta s upon में n1 equal to 1 minus में sin square phi की पावर में 1/2. Now if I see the limiting case, means if I say this is a maximum angle at which the ray enters into the optical fiber cable, so that angle will be known as the acceptance angle for the skew ray. It means that theta s will become equal to acceptance angle for the skew rays, and at this point limiting case, that this phi become what? Phi c. So you will see that cos gamma into में limiting case, for the maximum limiting case, theta s will become equal to theta as, and the phi becomes equal to phi c. So therefore cos gamma into में sin theta as upon में n1 equal to what? 1 minus में sin square phi c की पावर में 1/2. Now see, now as we know that the sin phi c is equal to n2 by n1, putting this value in this equation, you will see that the cos gamma into में sin theta as upon में n1 equal to will be equal to 1 minus में n2 square by n1 square की पावर में 1/2. That means sin theta as will be equal to n1 square minus में n2 square की पावर में 1/2 divided by cos gamma, and this is equal to what? We know that this is equal to what? Cos gamma into में sin theta as will be equal to numerical aperture of the fiber cable. Clear? Now see this one. Now from this equation, this numerical aperture of the fiber will be constant. From this equation you will see that the acceptance angle for the skew ray is always greater than the acceptance angle for the meridional ray. So the acceptance angle for the skew ray is always larger than the acceptance angle of the meridional ray, and this addition of skew rays also increases the amount of loss in fiber cable, as skew rays tends to propagate around the near edge of the fiber cable. It means the large portion of the number of skew rays will be trapped in the fiber cable and considered to as a leaky ray. So we always want to avoid the propagation of the skew rays, because it results in the maximum loss of power in the fiber cable, and that type of rays are known as the skew rays because it moves around the edges of the fiber cable. Clear? So today we have discussed about the numerical aperture of the fiber cable and the meridional rays and the skew rays and the acceptance angle for the meridional rays and the acceptance angle for the skew rays. The book which I have referred for preparing this slide, that is Optical Fiber Communications Principle and Practice by the John M. Senior. Thank you.